Okay. The second question of the quiz is actually straightforward because it tells you, say you have, oh no, I think it has C adsorbing, but it tells you that the first reaction is far right of equilibrium. So you can basically say that, you can basically write that. Then you have the second reaction, and at the third, which is the desorption. So the reaction is absorption limited. So the first reaction is the rate limiting step. So what you can explain here is the fact that if the first reaction is rate limiting step, however, any CS that you add, and I think some of you had the right answer, any CS formed gets reacted. So if any CS form gets reacted, there is not really a way for the pressure of C to inhibit the reaction. I mean, you could do the calculation, and if you do the calculation, let me see if I can see it. If you calculate the rate based on the surface, based on the adsorption being rate limiting, you will find this. It give you this answer. So it will give you this as the answer if you do it. So you'll find that if there is no B initial in the reaction, and you keep putting the initial pressure of C being higher, the rate's just gonna keep going up. So there is no inhibition. And so as you can imagine that for adsorption reactions, for adsorption limited reaction, the adsorbing species cannot inhibit the reaction, because that if it inhibits the reaction, it's not rate limiting, because whenever it adsorbs, it gets reacted. So that's essentially the answer, because it's not going to inhibit, because any form CS is going to get reacted.
So you get. Oh, you can go ahead.
No, it's okay. You go ahead.
Oh, so you get that rate law by solving for like the CS complex?
Yeah, you're gonna do this, right? Sorry. So you're gonna do, right? So you're gonna write this. But like I said, the reaction is far right, the first reaction, so you can neglect the reverse reaction, because otherwise you'd have K-1, right?
Oh, okay. So
yeah.
it said that in the problem.
And then, yeah, the problem says that the reaction one is far right of equilibrium, so you can
I see.
So then your S total is this, right?
Yeah.
So you can use equilibrium. You can use equilibrium to solve for CS and BS, and that's how you get these terms.
Okay. How come you don't have to specify the lowercase k as K1?
Oh yeah, that's what I meant. K1. Yeah.
Wait, so just to make sure, like the saying that the first reaction is going like all the way to the far right means that like it's irreversible, correct? Pretty much.
Yes.
Okay. And then another question is like, well, I understood that part like conceptually, but like I think I had a trouble like having the rate expression like back up my explanation. But basically, like in the notes you have there's like one word like surface reaction, surface limiting. So do you only use that if you specifically say it's like surface reaction, surface
is rate limiting? Yeah, like I think in that section I mentioned that 75% of reactions are surface reaction limited.
Okay.
But you can have reactions that are adsorption limited. You can have reactions that are desorption limited.
So that's when you know to if it's surface reaction, then that's when you use like the RS equals KS, and then the like you have the reactants in brackets minus the products over like
No,
the
so
equilibrium.
so if it's surface reaction limited, here what you would write minus RC is K2 CS minus K minus 2 BS. That would be reaction number 2. And your disruption is reaction number 3.
Okay, so surface reaction is when
Is
it
the
goes
surface
to
reaction.
site,
Yeah, so
site to site. Okay.
yeah.
And then, but they're asking for adsorption, and that's why.
It's the
And we
first
know
one.
that like the first one is irreversible. That's why we use that to make this reaction, and then you
Yeah.
have to do all of the like the steps to get like the site balance, and then
Mm-hmm.
oh, okay, that actually makes a lot more sense now. Okay.
Yeah.
I also had a question on the first one.
Yep.
So for the first one, I know that that A was 2, but for B, I got kind of confused because the number still changed, even
Well,
though
it changed very little.
Okay, so it's just a matter of like, did they change enough to like see a difference versus like are they
Yeah.
just kind of like error kind of thing?
The question did ask you what's the approximate order.
Okay.
So it could be 0.1, but we'll say 0.
Okay, I was just making sure because that like kind of threw me off, but that makes sense.
Mm-hmm. So I think some of you asked something where the surface, where the C, the pressure of C is limiting. That would be, for example, something like this. So if the surface reaction is limiting, you will have, you will actually see CS, C in the denominator. You will see that even if you only solve for even if you only solve for this, you will see that C is in the denominator, because let's say we were to say the surface reaction is irreversible. Let's say you had this. Okay, now this is your adsorption. Let's say your surface reaction is irreversible. So this is what you get, and this is rate limiting. This is your rate limiting step. So your minus RC is just K2 CS. And then you can use equilibrium in the first reaction, because the first reaction has to be in equilibrium if the second reaction is rate limiting. Because if they have the same rate, then there's more than one rate limiting step. If the first reaction is slower, the first reaction becomes rate limiting. So you can sort of how it goes back and forth. So you can calculate K1 is CS C times S. And then you can solve for CS. So CS is K1 C S. You can do a side balance, which once again will be 1 plus BS plus CS. You can plug everything in. So now you can see that what you will find out is minus RC is going to be K2 S total, what CS is, which is partial pressure of C, and it's going to be over 1 plus BS plus CS. And this basically shows you that the partial pressure of C, so it should be partial pressure of C, PC. This shows you that inhibits the reaction pretty much. That's sort of the idea.
If it was on the denominator, would it inhibit?
So if the pressure of C shows up in the denominator, it will inhibit the reaction as you increase pressure of C. Yeah.
Got it. And then last thing, I just wanted to clarify the pentane isomerization that you did for like an example. That was an example of like absorption limiting, right?
No, I think that was an example of surface reaction limiting, but with different type of surface reactions.
Okay.
Yeah. Different types of surface reactions. So they had one of them was a dual site, or one of them was a single site, the other one was a dual site, and it showed that the denominator was either not squared or squared. So, but one thing to keep in mind, guys, the way you go about solving, let's say, rate limiting step systems is exactly the way we did for enzyme reactions. It's just the way we speak about it is different. Now we say adsorption limitation, surface reaction limitation, or desorption limitation, but the way you go about solving it is the same. You know, you still write out that rate limiting step, you solve for the other steps using equilibrium relationships, and you plug everything in the site balance. It's the same thing every time.
Can you scroll back up to where you derived the rate law for the quiz? I'm still kind of confused on how you got it. Like, I understand where you're talking about any CS stats form get used.
Yeah, so let's solve for CS from reaction 2. So K2 is this, right? Yeah. And now, well, let's solve for BS in reaction 3. Okay, so then you have okay, so you can take that and put that here. Make sense? Because this is this, you can just do that. So that's how you get your total site balance. You can solve for S. You can solve for S in there. I skipped 1 or 2 steps really, but does that make sense?
The S back into the
yeah, and then you plug the exactly. You plug the S back in here.
All right, thank you.
Mm-hmm. Okay, so let's now do a quick. I think I answer. I think you would. So Melissa, I think it would just be recognizing trends. So in the exam on Thursday, it's going to be the same idea. So you can recognize trends instead of trying to compute anything, because the computing would need for you to graph it, to use Excel or something. So you wouldn't have to do that. Okay, let's see what we've gotten. Okay, let's do our. I think one student graciously asked me to sort of go through sort of an algorithm, but it's not exactly that. I sort of came up with it this morning. When you look at rate mechanisms, to sort of how to think about them, and it's essentially a review. I just wrote about a page and a half or so of points to think about, and that should help you. I hope it does. But then I also will put the solution to the exam, to the past exams, and that should even help you. So essentially, we'd call that a decision-making tree. Really what we're doing is thinking about what kind of problems have we solved and how did we solve them. That's pretty much what we're looking at. So the first thing we looked at is that you're given a mechanism. So that's the easiest approach. You're given a mechanism. 1, 2, you're told to use SSA or rate limiting step approximation. You're told to do it. So that's pretty easy. The way you're told to do it could be, for SSA, they could say the reactive intermediates, these things are reactive intermediates, or these species react as fast as they are formed, so that you know that they are basically at steady state near concentration 0. And the way you would look at rate limiting step would say something like, oh, reaction 1, reaction 2 is rate limiting, or it could say the adsorption or the desorption or the surface reaction is rate limiting. So basically the wording of the problem suggests what is rate limiting. Okay, Now, in both cases, SSA or rate limiting step, if a catalyst is present, you have to do a side balance. If you have, instead of a catalyst, you have a radical or a solvated ion. See, that's different. So that's the solvated ion would be, you would think about it in steady state approximation because it's not a catalyst. It just happens to be an intermediate that just gets formed. So you do a side balance. And within that side balance, there's a concept of the MARI, or most abundant reactive intermediate. So what that helps you do is nothing to do with what reaction is rate limiting. What this tells you is that in your side balance S star, S total, you have 3 sides, of course. Let's say you had this sort of thing, and you're told that AS is the most abundant reactive intermediate. That means, oops, this is BS. That means this is 0. So all it does is it simplifies your total side balance. What it also means is that B is not really adsorbing, meaning that BS complex is not quite there. Okay, so that's what that means in any sort of, it's nothing to do with rate limiting step. It's just a way to simplify your calculations. Okay. That's one sort of approach that we've looked at. Another approach we've looked at is we looked at surface reactions. So we'll look at gas phase, catalyzed, heterogeneous reactions. And they can be limited at different steps. They can be adsorption limited, surface reaction limited, or desorption limited. So they could be limited by different things. However, we didn't talk about this. There are cases where there is no rate limiting step really, because the rate limiting step could be rate limiting at different conditions, like in real systems. Like some conditions, the surface reaction is limiting, some conditions, other things are limiting. So in these cases, you'd be using the steady state approximation. You wouldn't be able to use rate limiting step because there isn't actually one. It could be multiple of them in different ways. But the one thing we did.
Can I ask something? So for the part B, that's the one that we did on the quiz that we were kind of working through, right? This is the method. Okay.
Yeah. Just giving you more like in depth, but it still uses the same idea as A. It's the same idea, but just using it. The nomenclature is different. For surface limited reactions, we had 3 types of surface reactions. 3 types of surface reactions. We can have a single site. Say you have A adsorb reacts to form B in the same site. You can have a dual site where you have A adsorbs needs a new site to give you B adsorbs plus S star. So it could have to need a different site to react, an adjacent site. Or you can have an Ayler ideal where A is adsorbs, but B comes in the gas phase. And then let's say now you form C, right? So that would be another type of surface reaction where only one of them adsorbs, the other one sort of goes in the gas phase and hits it. So yeah, so that's sort of, if you're given the rate, if you're given the mechanism and you're told some of this information, you can be told, this is the MARI, this is the rate limiting step. So you can go, and then from the mechanism, although you might not be told which type is happening, but you can tell. It will just tell you when you get your results. You can sort of confirm that your result is correct. And we'll talk about that in just a moment, what your results should be depending on what type of reaction, surface reaction is happening. So yeah, so the third sort of guideline is now talks about evaluating rate expression or hypothesize. I'll put them in the same category. So this is getting a little bit talking about some of the data analysis. So we'll do C1. Let's say you're given a rate versus C data, right? So we've talked about this. If you're given rate versus concentration data or partial pressure data, you can plot a linearized rate versus concentration or partial pressure, right? I'll just call it PI, CI. Okay, you can plot that. And then if you linearize it, you can plot it, you can calculate the constants based on the line, because it's some of the slope and the intercept are all going to have a value. You can calculate those. And on the exam, I'm going to ask you to linearize a rate equation to then, you don't have to calculate, you just linearize it to show how you would go about getting this data, information from the data. And now if you're given time or space-time versus CI data, you can do two things. If rate equation that is you assume, remember, we're assuming it, or you derive from mechanism, if you can integrate it, can be integrated, then plot time versus CI, or some form of time versus CI. And there's an example that we went through to think about, what do you plot? I mean, we found out that you'd have to plot natural log of CA over CA naught over CA naught minus CA versus something like T over CA naught minus CA. So you have to plot that to be able to get the constants out. So you can think of how do you manipulate that? How do you can be integrated and linearize? So the question can be, how do you linearize that integrated form to know what to plot? So that's one thing you can do. But if you cannot integrate the rate expression you assumed, if you cannot integrate it, for example, if it looks like this, if it looks like this and you have time or tau versus CI, then you have to derive RAs using some of the differentiation methods. So you have to use differentiation methods to calculate R's from time and CA. And we looked over 3 different ones. We had a polynomial one, we had a graphical one, actually 2 graphical ones to calculate minus RA from CA and T. Okay, so that's pretty much the approach. Whether or not you'll be tested on this on Thursday, that's at my discretion, but I'm just sort of giving you a big picture of what we actually did.
Professor?
Mm-hmm.
I had a question too about like when you're talking about earlier about like absorption limited and surface reaction limited and things.
Mm-hmm.
When was it? I just don't understand the difference between like So when you say like synthesize a rate law, right? And that's when you like you have like the surface, let's say it's surface reaction limiting, and then it's like the negative for pentane isomerization, you did
Mm-hmm.
like the Ks and then N S star minus I S star over Ks, like that one.
Mm-hmm.
But then you like found the expressions for the reactive species and like substituted that and did a site balance. So what's the difference between like that final thing that you get after you input all your site balances and then that first one that you like just start out with?
There is it's just a final form of it, because in the first one you cannot calculate the concentrations of these of the reactive species. You cannot calculate them.
Okay, got you. So it is
Yeah,
the rate law. It's just
yeah, it's the rate
start.
law.
Okay,
It's just when you first, you can't know what the CS is or what BS star is. You can't know that. You can only know your partial pressures.
okay. I was thinking of something different. That's why I got confused. Thank you.
Yeah. All right. So now we're getting more into a little bit advanced move. So now you understand a little bit of surface reactions. You understand how to derive the rates. You understand given data how you could plot it to get some of your. So can you? The question is, can you linearize this? And the answer, yes, you can. I'm gonna assume that you can because we did something similar in class. So now we look at something a little bit more. Let's get a bit more advanced move. We're almost there. So now we're gonna start looking at evaluating rate expressions. So this is what I would call working sideways or working backwards. So this is working backwards, working sideways. So we looked at, so we can, let's say C2-1. And this is gonna go back to something we talked about at the beginning. So let's say you have a surface reaction limited.
Professor,
Yeah.
I think where you had the ln Ca over Ca naught, the denominator is Ca naught minus Ca naught.
Oh, well, yeah. I was just giving an example. I think that, you kind of, you know what I meant, right? Yeah. Sometimes my fingers get a little jazzy, and they write something that I'm not saying. So yeah, so let's say now we get to, let's say, thinking about what your reaction rate expression should look like. So that's really what I'm saying. So whether or not it's from a mechanism or from data. So what could it look like? So let's say we have a surface reaction limited reaction mechanism. So that dictates what your reaction rate is going to look like, right? In the same way that absorption limitation dictates what the rate expression looks like. So it dictates that. And we talked about, for example, if it's single site, dual site, LO ideal. If it's only, say, if it's absorption limited, you have a different. Now, if you do a couple of examples, you can start seeing some things. So the surface reaction limited one, I've given you guys a table, depending on if it's single site, dual site, or LE ideal, what the denominator is gonna look like. So you have this sort of idea what's gonna happen. But now we can, if you have adsorption limitation, you know that the adsorbing species itself is not gonna be in the denominator. So you know that. Now, the question I have for you could be, what if you have a desorption limited system? And I can ask you a question about what do you think is going to happen. You can sort of think through that as well.
Professor.
Mm-hmm.
So like in this case, when you say like working sideways and backwards, so like that would be something, or wait, maybe not that. That's not what I'm thinking of. But like if you were to give us like the data like you did in number 1,
Exactly.
and like how would you know that if, because like we were able to like determine the order of the
Yeah,
react.
that's because it's a power law. Now, if it's Langmuir and Sherwood, I'll give you some data, and I think we did this yesterday, right?
Okay.
Or yeah, I'll give you data, and you could say, okay, now if I fix 2 of my species, and then the third one is changing, what is happening to the rate? So you can, it's but like I said, working
Okay.
a little bit backwards.
Gotcha.
So, and then you don't actually have to, you don't have, so here's what you would do. Let's say you don't know anything about the reaction. You run a bunch of experiments, you get the data, you analyze it, and from the data, you hypothesize, oh, this is gonna be a duocyte. And a duocyte, we tell ourselves, okay, this is gonna look like this. So this reaction is A plus B goes to C. So you say this is gonna look like this because this is a duocyte, because the data is telling me that's what it should look like. Now, how do you know to look for something like this in the data? You would set up experiments where you have partial pressure A, partial pressure B, partial pressure C, and then you would have different runs. This is your run number 1, 2, 3, 4, 5, 6, and 7, and then you would have your rate. And let's say now the reason why you would use a differential, in this case, you could use a differential PFR, because a differential PFR, as we described, is an initial rate. It's got very little catalyst, and it's got an initial, like whatever rate you see at the beginning is proportional to the inlet concentration or pressure. So let's say you fix A, you fix B, and you change C, and then the rate, let's say the rate basically goes, let's put 8, let's put 10. I'm gonna put a bunch of points. Let's say the rate goes up. Let's say it goes 0.1, 0.5, 0.7, and now it gets 0.7, 0.7. So that means what happens if you graph it, if you write C, the rate's gonna go up, it's gonna flat now. So what that means is, so what we did here is say we fixed P and PB at a certain low number, and we are moving this higher and higher. So eventually these terms are going to drop, becomes too small compared to PC, right? And then you'll say to yourself, okay, it looks like it plateaus. Oh no, let's say no, that's a mistake. I didn't mean to do that. That's a mistake. Let's rephrase this, because PC is not the right thing. Let's say you start with let's say 0.8, and then you have 0.7, 0.6, 0.5, 0.1, because C is a product, so we need to make sure we don't. So then you basically draw this. So you know that PC is in the denominator, because as you increase its partial pressure, the rate's going down. You can have a system where, let's say now you have a system where, now let's say we're fixing, let's say we fix 2 things, A and C, and we start changing B. So if we start changing B, we go again. So we do that, and then we start seeing the rate go up. Say the rate starts at 0.1 or 0.05, and then let's say it goes 0.2, and then let's say it goes 0.7, and then it gets to 0.8, and then it goes down to 0.3, and it goes down again to 0.1. So what this means is that if you plot it, you get a maximum. So what this tells you, at least at first, is that this the pressure, this term KBPB goes up faster than the term KPB. So that means it's likely squared, because if it wasn't squared, it would look like this. It would be 0 order. So because the denominator is squared, most likely that means this term goes up faster than this term, so you get a maximum. So you see, that's how you would go about doing it. Does that make sense? So you could first, the data could tell you what kind of rate expression you get. So that's what the data would say. You could verify it. It could be wrong. right? Now, to verify this, you'd have to, we talked about this really quickly, but not too much. You talked about this very quickly, but not too much. And let's say that you have two competing. Let's say from the data, you've developed two competing rate expressions. So you aren't too sure. Let's say you decided, okay, I'm gonna choose this guy. Now, once again, we don't know what KB, KC, and KA are, and that's why we need to linearize to do all the calculations. So let's say you have this, and then you also have, you tell yourself, okay, maybe it could be, instead of that, maybe it's this. Actually, maybe it's just an Early ideal because B is not absorbing. Maybe it's this instead. Now, what you do is you would look at your measured data minus calculated data. So the way you would get calculated data is by linearizing these, getting the constants, and then calculating how much you get. So you basically see how far you are. So you would basically get this rate data using things like solver. You would basically say, okay, I linearize the data, I plug in and I tell solver, minimize my errors to give me constants. And solver will do so, regardless of, solver and Excel will do so, regardless of the form that you put in. But then you have to tell yourself, if it's not very obvious which one is best, you have to make, this is a parity plot. You have to say, okay, my measured data, this is calculated data. For the best plot, it should be on a straight line. If it works, if it doesn't work, it should be solemn all over the place kind of thing. So this is essentially a parity plot. Similarly, you can have a residual plot. Where you plot, and then you basically plot the difference between them. Okay. So you can plot what you measure versus what you calculated, or you can plot the difference. If it's randomly across 0, that means it's pretty good. But if it happens to be something like you have a trend going, down or up, probably means it's not the best. It's not the best fit. These are essentially some of the statistical analysis. Now, on the exam, you won't be asked to compute it, but you could be given a plot comparing two rates, if that's the case, to say basically, oh yeah, this one is the best one, this one. So now you have to think about that deviation, right? The deviation, you could have two rates where the deviation is, let's say 0.01 or 0.02, and then the other one looks about the same, but the deviation is like 0.7 and minus 0.7. So you would know that the one that does the lowest deviation is probably correct. So that's also another way to look at it. This is in your like chapter 6.4 or something. So it's in there. You can read it. It's pretty straightforward. What they did in there, they compared fructose isomerization using two different rate expression that they guessed. But it was very obvious because fructose isomerization goes through Michaelis-Menten. So that's pretty obvious. That if you use a power law, it would be very different. But something like these two, it's not that the difference is not that drastic when you look at the different plots. So you have to be a bit more attentive. Okay, now if for example, you calculate your Ka, Kp, and Kc, it may be that Kc is very small compared to Kb. So you can say things like, okay, I can drop that term because Kc is always very, very small compared to Kb. So, so that means your desorption step is very fast because Kc is an adsorption equilibrium. So that means your desorption is very, very fast. So you can drop that term. So you could be asked, for example, these types of qualitative questions, if it comes to be, what terms could you ignore?
Professor,
Mm-hmm.
for like, I know yesterday in office hours, you were like going over some of the graphs like you just did, but I have a question because like you had assumed that the equation was like Langmuir Hinshelwood or
Well, yes.
or like with the squared on the bottom, but like I understand that, and then when it's not squared, but how do you tell the difference between that, like when you have a denominator versus when it's a power law, just like a regular power law?
That's a very good question, right? Because if you have a catalyst that has a surface reaction, it's most likely going to be a Langmuir-Hinshelwood. If you have a catalyst where the reaction is happening inside the pores of the catalyst, this is something we hopefully will get to at the end of this course, then it's going to be some combination of power law and some other type of thing. So now this reaction can be a power law. Do you know how you can make it a power law?
No.
If you can operate this reaction at very high temperature. If this reaction is exothermic, you operate at high temperature, all the equilibrium constants become small. Ka,
Gotcha.
Kb, and
Okay.
Kc become small, so this reaction becomes a power law.
So
See,
sorry.
Yeah, go ahead.
So for the purpose of like what we're doing right now though in like this section with like the catalyst, so most of the times like the experimental data that we're looking at is going to have like that model of, the partial pressures on top and then the denominator either being.
Yeah, so so that's what I mean to say here is that the rate expression changes because of based on the conditions you run the reactions, right? So this reaction, which is a Langmuir-Hinshelwood, you would expect it to be that form, but if you run this reaction at high temperature, it may just be a power law.
Okay.
So yes, you're right partially, but I don't think you should go ahead and cement that this is what happens all the time.
Okay.
You can't cement that as a way to reassure yourself to not be able to see anything different. But you can assume at least that these will go through a Langmuir-Hinshelwood if there is an adsorption and a desorption. But that does not mean ultimately, if you run this reaction at a certain condition, it might not obey that law. It may just be a different. It may actually go to a power law. Of course, that could be too. I'm not gonna ask murky questions like this on an exam, as you may imagine. But it's something for you to keep in mind. This is not set in stone every time.
Okay, that makes sense. Like
Yeah.
I was just a little confused because like we kept looking at if it's squared or not squared and like the data in regards to that.
Now the
I
data,
just wanted to.
maybe it might take me too big of a. It might take me too much work to get a data that transforms this into a power law.
Yeah. Okay.
But
I just wanted to
I-
make sure.
I have to come up with my own data points, and that may take me a few hours to get it right. Yeah, so that's essentially it, guys. I think I went 25 minutes over the time that I told myself I was going to do it. But yeah, that's essentially it. You just need to understand those things, and keep an open mind about them, because we've only really looked at a few examples. For example, you know what we did not look at? What if you have dissociative? What if you have a dissociative adsorption? So if you have a dissociative absorption, suddenly your first reaction here, if that's rate limiting, let's say this is rate limiting, your all rate 2 suddenly now is K1 A2 S squared. So now that's a squared S. So So now that becomes another thing, right? Minus k minus 1 as squared, right? So, you have a couple of things to think about. Anyway, that's just sort of, telling you, we've seen some things, but you can keep an open mind about some other things that can happen. We have only looked at some examples that are, and in many cases, as I mentioned, there is not really a rate limiting step in the reactions, and then in real life, you have to have a mixture of steady state approximation depending on the conditions you run the reactions at. So, yeah. All right, so let's stop there. Let's take a couple minutes break. The one thing to keep in mind now, I didn't go through that, but you can do some examples back and forth. Like you can take an example yourself. You can take an example like this. You can work yourself. You can work out a few things. Let's say you can take something like this. And then solve it for adsorption limited. Solve it. Surface reaction limited. Desorption limited. And then compare the rates. See what they look like. And see what you can make of them. And you can come up with some thoughts. You can say adsorption. A, not in the denominator. So it doesn't inhibit with increasing. Desorption limited. What happens to what happens if you increase A, if it's a desorption limited? You can already answer this without doing any calculation, but I assume that you could calculate it and find what's going on. Surface reaction, we went through examples of that as well. So, all right, let's take a couple minutes and then we'll come back in 5 and we'll continue talking about our current topic. Do ask questions if you've got them in the meantime, though, because I'm not actually going anywhere.
Professor, I had a question. I wanted to ask if like recycle ratios were on this exam.
It's study for it, but it's leaning towards a no.
Okay, I just wanted to make sure because I have like, I don't know why, or I think this was before you had decided not to like put them on the last exam, but I have like the exam 1 stopping at right before autocatalytic reactions.
I know.
Okay.
I know. I mean, it's leaning towards a no because of the quantity of material we can actually ask questions about.
Okay.
But yeah, because for recycle reactors, we've actually done the 2 things that can be done with them. One thing is to calculate the volume of the recycle reactor. The other thing is to calculate the recycle ratio.
Yeah.
So we've done both of these things. So
yeah,
asking you that on the exam and in a way that you can solve it, because if your recycle ratio optimization is very difficult to solve if you use the wrong numbers.
Yeah.
So there's no way I'm going to ask you to do that on an exam.
Okay.
Yeah. So the only thing I can ask you is to calculate the volume of a recycle reactor, but it's a straight up equation. So it's not really that exciting to me at the moment. So it's leaning towards a no. But you will have a pressure drop in the reactor. It may or may not be linked to a rate mechanism. So that's up to you. I don't know if I have to get to that, but it may or may not be linked. But it's not, it's not like anything you haven't seen. You've seen it. It's just turned around a little bit differently.
Thank you.
Dr. Denard, I had a question about the quiz. So for number 2, would you be able to have, or could you tell that it's an adsorption limited reaction based on the problem statement if you hadn't had explicitly told us?
I would have to explicitly tell you.
Okay.
Or I could, I could do like one of those advanced move and tell you that it was found that A does not inhibit the reaction, right?
Okay.
So you could start now thinking backwards. It's the same thing with Lucic. It's the same thing as giving you data, right? Does that make sense?
Yes, thank you.
Yeah. Yeah, we've fallen behind a little bit, and that's because although I didn't intend to spend as much time on rate mechanisms, but it's also very fascinating to teach and to get feedback from, because this is the first time I'm teaching it in that depth. So we're fallen behind by probably half a lecture at the moment, maybe a lecture, but we'll try to catch up. But if we don't catch up, that's okay. We'll use the last day that is empty at the moment to teach at least half of that lecture.
Dr. Denard,
Yes.
another question I had was that would you have to tell us if it's like competitive inhibiting or like non-competitive inhibiting?
See, I like your questions. They're very good, but no.
Okay.
I will not have to tell you. So the question is, can you tell from the problem statement? For example, should I give that example?
Yes.
Let me think.
Is it a good example?
Let me think about it. Okay, so if I say that, you ran this reaction and you expected these numbers for, let's say, an enzyme, and you got those other numbers, and then you ran the reaction in a different buffer, and then suddenly you're getting the numbers you're expecting. Say that's what the case is.
So
Say, I'm just thinking out loud because I do protein engineering. So say you run this reaction in tris buffer and you get some numbers and you're thinking, what's going on here? It's not what I expected. And then you decide to run this reaction in heaps buffer. It's a different buffer, or maybe acetate buffer. And then you get the constant you're expecting, Km, Kcat, and all and the likes. So you can tell yourself, okay, let's say your Kcat changed and your Km changed. Both of them changed. And you can say, okay, well, what type of inhibition could that be? Right? So you would go back to your notes and think about, okay, why is both Kcat and Km affected? Or you could say, why is only Kcat affected? Why is only Km affected? So these are types of inhibition that mechanistically are verifiable, because we looked at the mechanisms, the different sequence of reactions. So we looked at all of those, right? So that's how it would be formulated. It wouldn't be telling you, like on the homework, it says derive non-competitive inhibition. No, that's just algebra. We need to think about what is changing. Make sense?
Yes, more or less.
Yeah, no, it will be fine. Like I said, right now the exam has about 6 questions, and the way they're formulated is that you will not completely bomb it. So there is not really a way to do so, because there's many questions that are short and they're not on like an amazing number of points, like 15 points for this particular one, or 10 points or 5. So you can't really completely bomb it. That's a good thing. But it's harder to write this exam because I have to come up with lots and lots of questions. Okay, now that we've taken our break, let's go back and get excited again. Now, the thing that last time, I'm gonna actually write it all out so that we can be on the same page. So last time we introduced multiple reactions. Chapter 7 in your book is amazing, by the way. you should look at this, especially the examples that they go over for different types. We're doing something slightly different from the book, but it's just supplements the book. And the book is great as is. We're just doing a little bit extra because I like to, and I have some really nice concepts to introduce that the book doesn't introduce, so I'd like to really go about that. But yeah, the book is great. You should read it. So the first thing I'd like to say is, are these lectures broken down? The next 2.5 lectures. So this is the first thing I want to say. What we did last time, we defined selectivity and yield. We saw that selectivity can be defined differently depending on what type of reactions you have and what works for you, because it could be that defining selectivity based on, reactant works best, based on an undesired product works best. It could be based on atoms. Maybe like if you have a reaction where you have lots of alkanes that are being burned, you could define your selectivity based on carbon atoms that are being fed. How many moles of carbon? So that's easier for you because you have lots of things that have carbon in them. Ethane, methane, propane, butane. You have lots of them, so you just do a number of carbons. So okay, then the other thing that we started doing is parallel reactions. So we started with parallel reactions, not series reactions. The reason is parallel reactions have a lot more things in it that we can explore. Series reactions can be a little bit tricky. That's why we're doing parallel first. It's clear what we'll be doing. But series can be a bit tricky. If you look in the book, they start with series and you look at all the graphs they make, and there's so much to unpack in there, but they don't unpack it in there. So that's something that I think it could be a little bit better, but it's okay. So we looked at parallel reactions. The way that these lectures are going to work, we do a qualitative thing, right? We looked at the parallel reactions. We say, if you have two parallel reactions and you want to maximize selectivity for your desired product over your undesired product, and we also define instantaneous versus point. And we're going to come back to that today, if I think we have time. Versus point. So we have to that. So let's say we have parallel reactions and we say, okay, instantaneous selectivity is the ratio of the rates of each reaction that you're comparing. And then you're saying, okay, depending on the power or the overall order, then you have to decide, do I run a CSTR, do I run a PFR, do I run a semi-batch, do I run? So you can review that from last lecture. And I think on the University of Michigan website, they have a few more examples, and I'll put a link to that at the end of class. So you can go in and do all these qualitative approaches. They even have things with membrane reactors, which we barely touched on, but you'll get the idea once you get to that. So we looked at, because our plan is, can we maximize selectivity? That's one type of problem that we deal with. One type of problem is maximize selectivity. So we can do it qualitatively. What type of reactor would be best? What type of feed conditions? What kind of temperature, could be best. Now we can also do maximize the selectivity graphically and numerically. So this is what we're going to do today. And then the next set of problems you can have, which are actually a lot of them in subchapter 7 in the book, is, can you calculate selectivity given these conditions? Like you have a reactor with 1,000 kilograms of catalyst, and you feed A and B at this molar flow rates, and you have this temperature and this pressure. This is the value of K, for each reaction rate constant for each reaction. So what's the selectivity from that combination of data? And what happens in these particular systems is you'll find that you have to use either MATLAB or GOLSEEK or Solver because you have multiple equations now. And this is now, we'll go back. We're going to get back to this by, after exam, that we're going to solve these more quantitative, calculate selectivity from data we're gonna solve them using MATLAB, using Python and GoSeek. And we are also going to graph them and show how things change over time, but we're doing all of this at isothermal, okay? So we're not introducing big temperature changes with multiple reactions. This is something that's possibly on your exam 4. This is not coming up right now. Now, the one thing we're doing is we're looking isothermal multiple reactions. On the one side, we're looking at maximizing selectivity and how you can do it qualitatively, graphically, numerically, and calculating those selectivities given a bunch of data. These are the 2 kinds of things we're looking at. So that's pretty much what these lectures are about. We do the same thing for parallel reactions and reactions in series. So that you get an idea of how the structure of the lecture. So you don't get lost, I would say. So we look at parallel reaction anyway. Reactor choice, we have qualitative. So this is maximizing selectivity. The question is maximize selectivity in reactor type. So we can say, what's the maximum selectivity you can get in a CSTR for these reactions in parallel or in series? This is qualitative and somewhat quantitative. And then you have another set of problems. This is from our maximized selectivity. Another problem is to calculate things like catalyst weight, volume, selectivity, mole fraction. So these are things that are similar to what we did at the beginning of class. So, and then we do the same thing for series. Same approach. Okay, so that's it. And so today, the last thing we'll do are the quantitative examples using MATLAB, using Python and Solver. But in the book, all of the examples are amazing, like anywhere from 7.2 to like 7.7. You should check them out. They're good. And this is gonna be kind of the last bet that we do. We're gonna take some examples from the book. We're gonna bring our own. We're gonna put all together, and then we'll wrap this up. It's gonna be great. All right, so let's start it. All right. So now we are at parallel reactions. Last time we stopped at reactor's choice and feed choice conditions, and I won't go through that much because you can look at it. So let's say now you have 2 parallel reactions, just like we did before. And the question is, can we maximize selectivity depending on the reactor we choose? And D is desired, U is undesired. Okay. Maximize selectivity can also mean maximizing yield depending on how many reactions you have. But the first question we answer. So before we go, first question, very important. In a CSTR, S hat of say D over A. Let's say this is selectivity of D with respect to how much A is in there, is equal to S of D over A. The reason is because this is well mixed. This is your well mixed CSTR, right? The concentration of A, so you have A coming in, and then at out you have CD and you have CU. This is the same as what's inside. So that means the selectivity that at any point instantaneous is the same as the overall. So instantaneous equals overall. I'm just going to call it point so I can write it. It's the same thing. Point equals overall in a CSTR, okay? And if you remember, S of D over A is going to be CD minus CD naught over CA naught minus CA. Okay, that's what the overall selectivity is. Now, in a PFR, what is it? So that we're going to do a little bit of math here. In a PFR, it is not equal. And the reason it's not equal is because the selectivity is changing as you move down the reactor. So that means the instantaneous selectivity at any point along this reactor length, can call it Z, is changing. But what is the actual selectivity? And it's going to be a familiar refrain, and you will see what that refrain is. It'll be a familiar one. So the instantaneous selectivity, say, of R to A over A. Now, keep in mind, let's write out here what the rate is. We'll call it K1. I don't like KDs. I keep forgetting them. CA to the power of A1, RU is K2, CA to the power of A2. Let's say this is what we've got. Just a normal parallel reaction. So the selectivity of R with respect to A is the same as DCR. This is the rate d tau, right? Over minus DCA d tau, which is basically DCR over minus DCA, right? And that removes time from your analysis. This is what you would call a time-independent analysis. Actually, that's in the book. That's what they call it, but they just give it a name. So you've removed time or space-time from your analysis. So this is reactor volume independent because there's no space-time term. So that's equal to K1 CA to the power of A1 over K1 CA to the power of A1 plus K2 CA to the power of A2, right? That's just putting that. And you can now say, okay, so DCR, you can put CA on the other, minus DCA on the other side is minus K1 CA A1 over K1 CA A1 plus K2 CA A2 DCA. You can integrate both sides. So here you'd integrate from CR naught to CR of DCR. And you would integrate here from CA naught to CA of DCA. And this, I put the minus outside. And what you notice is that we are integrating the instantaneous selectivity. That's what we're doing, right? So this is this term here. I don't want to be writing it every time before I mess up a subscript. This is the instantaneous selectivity that we've effectively integrating.
What is the second term in the denominator? Is it K2C?
CA. I had a lowercase a, I changed it to uppercase a. So yeah, it's the same. So we basically realized that we are integrating the instantaneous selectivity.
Dr. Doug?
Yeah.
What is R?
Oh, I meant to say D.
All right, you had me like so confused there. Oh my
No.
God.
Yeah, I think I meant to say D. Thanks for pointing that out. It's because I took those notes from two different things. And in one there was R, and the other one it was D, and now I completely screwed up. Let's see. Okay, I think this is many R's I have to change to D's. All right. Now, a couple of things you can see is if you first thing to see if C D naught. So now let's make sure to do this right. Equals 0. So you can say that CD, so the concentration of D coming out of your reactor is, I put the minus sign in the limits. You see this? This is time. This is space-time independent. This is the first thing you can do. You can calculate the concentration of D coming out of a PFR, whatever size that PFR is. You actually don't know. You can find out after. But the first thing you can do, you can calculate the concentration of D coming out of the PFR based on the selectivity of the reaction given by the rates. Now, of course, here you need to know K1 and K2. Need to know K1, K2, A1, A2, right? You need to know those things. But that's the first thing you can do, which is very exciting.
Dr. Denard,
Yes.
how did you get the K1 CaA1 over K1 CaA1 plus K2 CaA2?
This is the instantaneous selectivity. Instantaneous selectivity is the rate is RD over minus RA equals S hat of D over A. Yeah, that's the definition of instantaneous selectivity. Now we also have that's in the previous notes, by the way. That's in there. Yeah. So this is your selectivity definition. Does that make sense? I hope yes. Okay.
Yeah, you're good.
Okay. So yeah, that's where that comes from. So now that's the first thing you can do. So of course, now if you were to really do that, it would be CD over CD minus CD naught, right? And that's equal to, we'll throw the minus sign in the limits to get rid of them. Let's say now we divide both sides by CA naught minus CA. If we do that, so divide, this is dividing both sides. What you notice, sorry, I'm gonna erase that. This is divide both sides. If you do this, you realize that this is overall selectivity, D respect to A. Yeah. So suddenly you realize something, the familiar refrain, that the overall selectivity of a PFR is the average point selectivity over the whole length of the reactor. Length also mean volume, catalyst weight. So same idea. Because if Ca is the exit concentration, Ca naught is the entrance concentration, and you integrate the selectivity, the point selectivity over that, and if you divide that by the limits, the difference in the limits, you average it. So it's the same thing we did, I think, for the we did the same thing for the recycle reactor. So it's a familiar refrain. Okay, so now how do we visualize that? So yeah, so one thing to note is that for CSTR, let me see where, let me go up a little bit. Okay, I didn't put it on yet. So this is for PFR, this is how you'd calculate concentration of D coming out. It actually is a function of point selectivity. For CSTR, you can convince yourself of that. CD minus CD naught is selectivity. See, I keep putting those R's. Sorry, guys. I'm copying my notes that I wrote I keep putting those R's. Times how much A has reacted. Does that make sense? How much CD you form is the selectivity, which is a percentage, because remember that the selectivity goes from 0 to 1, right? It's D with respect to the reactant, so it goes from 0 to 1, versus times the amount of A that's reacted gives you how much D you formed. So this is that for CSTR, and this is that for PFR. And of course, that's equal to S D over A, because instantaneous is equal to 0 for a CSTR, before I forget. So if you just know how much A is out there and how much E can, if you know how much A is coming out and how much D you formed, or if you just know how much A is coming out of the reactor, you can figure out how much D is made actually. But we'll get to that in a hopefully soon, but we may not do it today, but we might get there next time. But I'm hoping to go through all these concepts right now. So let's show this graphically, because we love to do that too. We love to do this because it hopefully puts it all in perspective. Well, we don't know, but we'll see. So let's say we have our S hat. We've written this before. I switched them accidentally. That's all right. You can rewrite this as that. You can convince yourself that's the case, but you can rewrite this like that. It's the same thing. Now let's plot it. So now let's make a plot. All right, let's make a plot. And let's say that A2 is bigger than A1. If A2 is bigger than A1, this plot is S hat of D over A, and this is CA. This is the plot. If A2 is bigger than A1, this plot is gonna look like this. That's what S hat is gonna look like if A2 is bigger than A1. Now we assume that K1 and K2 are in the same order in terms of, one of them isn't like 100 times faster than the other, but they're about, in a similar order. Okay, let's say that you start at CA naught. So we're gonna do this graphically. This is CA naught. And your exit concentration is CA. If you use a CSTR, your selectivity is actually right here. This is the overall selectivity CSTR. If you and then remember this, remember what we said, CD is selectivity times CA minus CA naught, so it's the rectangle. So if you want to know how much CD is formed, it's multiplying CA minus CA naught times S. And that tells you pretty much, I'm going to put in a different color to make sure we don't get confused. That is in the rectangle how much CD is formed. It's not the volume of the reactor, okay? It's just how much CD is formed. It's just graphically showing that. Now, let's say now we were to look at a PFR and we say that is the average. So it's going to be somewhere in between. Let's say it's here. Now, so now this is the overall, this is the average selectivity in PFR. Now, if you go back to what we talked about before, what we're saying here is that A2 is larger than A1. So what this is effectively saying that if you have A goes to D and A goes to U, and this has the, let's say this rate is KDCA, and this rate is KUCA squared. That tells you, we talked about this before, this is RU. It tells you that you should run this reaction in a CSTR to maximize the selectivity for D, which basically meaning that you should keep the concentration of A low, because when you do RD over RU, it's KD over KU CA to the -1 power. So you see how graphically it also makes sense. It all makes sense. So if you do it at PFR, not very good. Your selectivity is going to suffer. Now let's look at the reverse system, where if now A1 is larger than A2, the
Wait,
S.
Dr. Miller, before you move on, what was the green box again?
The green box is in the CSTR. This is how much CD is formed, because it's the product of CA0 minus CA times selectivity, right? This is this. This is just graphically showing you what this is. Does that make sense?
Yeah, thank you.
Yeah, but I will reiterate, it is not, as in the first part of class, we talked about this being like volume of reactor, 11 spill plots. It is not the volume of the reactor. It's just the amount of CD that is made. Okay. And now you've made less CD. You know, if you looked at this square, so I'm gonna make it a different color. Can I actually do that? Let's see. Oh man, this is not working. So if I go to the PFR, if I operate at this average, this is the amount of CD I make in the PFR. It's much less. Okay, let's see if I can go back to my color. Oh my goodness. So now I screwed up. Why is this happening? I don't like changing color, that's why. Okay, there we go, we're back. Okay, now if A1 is larger than A2, that selectivity curve actually looks like this. And now we can do the same process. This is CA, this is S, this is S, this is again D over A, okay? Because if we do S of D over U, you're gonna have either a straight line going up or a straight line going down, depending on the, depending on the orders. But this is as D over A. And this is important because we're gonna go and then look at, if we have some time, we're gonna look at something called the Trem-Booz reaction in the next 20 minutes or less than that. So anyway, so let's say you have the same process, you have CA0, so you're starting there and you're coming out as CA. If you have a CSTR, I'm gonna put that, I don't wanna change color, guys, sorry. Because every time I try to do it, my program just messes up. So if you do this in a CSTR, you're gonna come out right there. This is your CSTR. Now let me write it here instead. This is your CSTR selectivity. But if you do it in a PFR, where you once again operate at an average between the 2 points, because that's what we calculated, your selectivity is gonna be right there. This is your average selectivity for a PFR. So once again, you see that if A1 is larger than A2, you want to operate at high concentrations of A, which is basically a PFR. So you can see graphically how that makes sense. And then if we flip the script here, I'm gonna keep green for CSTR. This is your CSTR, and I'll put it red for the PFR. This is how much CD you make in the PFR. Any questions? This is exciting because that leads us to a slightly more complicated version where we have now 3 reactions in parallel. And this is the world famous Trem-Booz. Trust me, it is a cool name. You should say it a bunch of times. You should go around telling people you know something about Trem-Booz. I like that name. So the Trem-Booz reaction, what it is 3 reactions. So you have A goes to R, A goes to S, and A goes to T. And the classical one is saying that these are the rates. These are the rates for each of the reactions. This is just the classical Trenbos, right? Okay, so the question I'm asking is, what is the maximum concentration of S what is the maximum that can be obtained? Say in a CSTR. What is the maximum that concentration of S? You're given Ca naught equals 2 mole per liter, and these rates are per second, so that those Ks are inverse seconds. For example, let's say that's what you're given. Doesn't matter too much. Now let's make it minutes to make it more realistic. So the Ks are in inverse minutes. In terms of times, not the Ks. Times or inverse minutes. The Ks have different values. The different units. Okay. Well, you have 1 in a CSTR, 2 in a PFR, or 3 in a reactor system. So PFR, CSTRs in series, those types of things. So you can be asked that question. That's a pretty classical, very nice example. I really like it. So we'll take the next 15 minutes and we'll solve that. All right, now the first thing we're gonna do, so this is our solution. First thing we're gonna do is, what is S hat of S over A? This is 2Ca over 1 plus 2Ca plus Ca squared. And this is 2Ca over 1 plus Ca squared. Right? So that's just what that is. Give me a second here. Okay. So you've got your S hat. So you know that's the first thing you do. Now for CSTR, S hat is equal to S, and CS, this is concentration of S, is S times Ca naught minus Ca. So that is 2Ca 1 plus Ca squared times Ca naught minus Ca. So the question is asking you, what is the maximum concentration that you can obtain? So you have to do dCs dCa. So it's taking the derivative of that function. Equals to 0. So if you take that, you can put it in Wolfram Alpha. Don't try to solve it by yourself. And then Ca naught is equal to 2. If you do that, you find that Ca is 1/2 and Cs is 2/3. The one thing that I wanted to show you before I continue, and I think I forgot to do it, is that if you graph S hat of S over A, if you graph this function, you can see that this function is going to go through a maximum and it's going to drop. Okay, so this is your Ca naught, and your Ca, this is 2, so we can say this is 1 and this is 1/2. This is your Ca equals 1/2, and this is the box you're going to make. This Cs This is the maximum amount of CS you can make inside this reactor in a CSTR. Now you can notice that there is a maximum selectivity here. This is not where we are. We're basically maximizing the rectangle. To maximize the rectangle, you basically have to take a derivative of the function that gives you the rectangle. So essentially this function. Okay, so that gives you some number. So this is what would happen in a CSTR. So the next question is, what would happen in a PFR? So we're going to go back to our equation where CS is equal to. Now, let me draw this again so you can get an idea of what's happening here. So if you think about the maximum amount of S you're gonna get is gonna be the area under the curve, right? That's the maximum amount you're gonna get. So that's basically going from 0 to CA naught. So you integrate from 0 to 2, and you integrate this is the formula we derived earlier. So if you do this integration, you'll find that CS is equal to 0.867. This is molar, by the way. So this is 0.6, this is 0.8. You can see that you basically make more. You make more S in the PFR because you're operating at an average selectivity that's higher than in the CSTR. It's very cool. And you can calculate the selectivity as well. You can basically say that, and this is CA equals 0, okay? The selectivity, the overall selectivity here, right, is going to be CS minus CS naught over CA naught minus CA. So it's 0.867 divided by 2. And that gives you 0.43. You can calculate it up here as well. So it's going to be, for this guy, is going to be 0.66 divided by 2 minus 0.5. I don't know what that is. Actually, I had not calculated it before, but it should be less than 0.43. Let me see, what is that? 0.66 divided by 1.5. It says 0.44. That's interesting. That shouldn't be 0.44. Maybe it's just so close that it doesn't, because the numbers don't work out because they're so close to one another. Maybe I made a mistake in calculating. Yeah, it turns out that these are very close to one another. So I'll have to get back to you on why that is. And maybe if I change the numbers for the rates instead of 1 and 2 and CS squared, if I change them, maybe that will make a bigger difference. But nonetheless, here you can see that you can make more of CS in the PFR. So let's keep that. Let's put a pin in that for a second in terms of selectivities themselves. So I may have made a small mistake in it, if anything, but I'll get back to you on that. Okay, now the third question is asking a series of reactors and then how you would put them together. So you can draw this again. Now, what you want to do is saying, okay, well, if I'm starting from CA naught, if I use a CSTR first, I can operate the CSTR at the maximum selectivity. This is X max. I can operate at this X max. So you can say, what is S max is to take to equate the derivative of the instantaneous selectivity to 0. So if you do that, it's taking the derivative of CA of 2CA 1 plus CA squared, right, equals 0. That gives you a CA of 1 and a C and an S and an S star and an S hat of D over A of S over A of 0.5. So you're saying that if you operate in this at this particular CA equals 1 and S of 0.5, that would give you a CS. You can size a CSTR there. So by doing so, let's see, where am I? Yeah. So if you put the CSTR first, it's going to operate at this exit selectivity, so the highest. It depends, of course, on what the curve looks like. So this curve looks like this, so we're going to do it that way. So if you put CSTR first, then CR is S times CA naught minus CA. And that's 0.5 times 2 minus 1. And this is 0.5. This is the concentration of CR that's coming out of the first reactor. And for good measure, you can size the reactor. If you remember, tau, you can actually get the space-time, is actually CA naught minus CA over minus RA evaluated at CA. This is the design equation for CSTR, which is liquid phase at constant density. And that is 2 minus 1 divided by 1 plus 2 times 1 plus 1 squared, right? This is the overall rate of A. And that should give you a quarter minutes. So you see how we actually can size the reactor pretty straightforwardly by knowing very little information, really. You just know the Ks for your rates, and you know the and you know the concentration that you start with. So if you can look at your PFR. So yeah, we'll be done in just a minute. So if you look at your PFR, you can say that CR, the PFR is coming in second. So from 0 to 1, because this is basically so this is what's going on here. I can draw it out for you. This is the CSTR, right? It's the square, right? And this here is your PFR. It's not the volume of the PFR, keep that in mind. It's where the PFR is operating. So to give you that how much CS you're getting, essentially. Now, one thing to keep in mind is that the CSTR is operating at this selectivity. The PFR is going to operate at some average selectivity. So that means the overall reaction is going to be operating at some selectivity that's right there, the overall system. Just to keep that in mind. So if you go from 0 to 1, and then you look at 2CA over 1 plus CA squared dCA, if you integrate that, that gives you a CR of 0.38, right? That gives you CR of 0.38 molar. So you're making a total of 0.88 molar, which is slightly higher than the PFR by itself. Slightly higher, CS. See, I keep doing those R's. I apologize. This is CS. Once again here. Okay. Now you can also do the tau. So d tau is actually equal to minus dCA over minus RA. This is a very simplified version of the design equation, which is equal to 1 over 1 plus CA squared dCA. And then you can integrate both sides, here from 0 to tau, here from 0 to 1. And that gives you a tau of 0.5 minutes. So you can size reactors, you can get the concentrations of things coming out, just kind of looking at, without introducing space-time as one of your variables in the beginning. Sorry, I'll keep it there, see if you can copy it. So you don't introduce space-time as your initial variable. You remove it from your equation by doing a time-independent analysis at first. So if you go back, if you look at what I mean by that. So the very first thing you did is right there, we've removed space-time in the equation. Or yeah, so from here, for example, we've removed it. So it's not there anymore. And by doing so, we can calculate concentrations independent of the reactor size. We don't need to know the reactor size. We can just know what's the maximum selectivity you can get, what's the maximum concentration you can get. You know, so you can basically say conversion. So if you were to say, okay, the maximum conversion you can get is 2 minus 8.6 divided by 2. So your conversion, the maximum conversion you can get towards S, which is then essentially yield. So that's the maximum yield of S. You can calculate that. So yeah, that's pretty cool that you can do that without knowing what the reactor volume is. But you can actually calculate the reactor volume after you've done some approximations. We could also have calculated the reactor volume in part 1 and 2. I just didn't do it because part 3 essentially can do both. So you can calculate reactor volume in part 1, part 2, that's fine. But you can essentially just showing it here as a combined version. Okay, do you guys have any questions? So I hope I'll have another office hours tomorrow. If you want to stop by I'll post the answers to 2 of the exams this evening. The third one I actually have to solve because I actually don't have the answer key. I can try and solve it and post it on Wednesday morning or Wednesday afternoon. And yeah, so we're stopping here. Exams Thursday. What we're gonna do after this is we're actually gonna look at reactions in series now. Okay, we're gonna look at reaction in series. And we are now, when we go do the same analysis, like similar analysis, not the same, with reactions in series, which is a shorter version, then we're gonna start looking at quantitative, the other side of the problem, which is given data, numbers, can we calculate selectivity? And we're gonna use Solver and Python, and I'm gonna show you, we're gonna talk about semi-batch. So review this, what we did today, and for next time we meet in a week, it's really going to be essentially from the chapter 7 in the book, starting from, let's say, section 7.2 all the way to the end. We're just gonna work out the problems, explain them. I would introduce 1 or 2 of my own problems, but we're gonna do everything using Python and Solver, so that on your homeworks, you can do that as well. And yeah, so that's kind of the approach. So we'll spend the next lecture next week on that, and a little bit of it next, the lecture after will be about a lecture behind, but we will catch up later. Then we'll be introducing heat effects, energy balances and things like that, which is even more cool, more exciting. Okay, that's about it. If there's any questions, I will see some of you tomorrow, and I will see some of you in the exam.